Two-way ANOVA. Analysis of variance is one of the core concepts of linear models, and we have already seen that an analysis of variance model is a special case of linear models where we have only categorical inputs into the system. If the number of categorical inputs happens to be 2, then we have two-way ANOVA. The theory is remarkably similar to that of one-way ANOVA, except that here we have to worry about whether the two inputs interact with each other. In this module, we are going to take a look into that. Two-way ANOVA. In a two-way ANOVA, the effects of two factors or treatments can be investigated simultaneously. Two-way ANOVA also permits the investigation of the effects of either factor alone or of the two factors together. Thus, this is useful in a situation where you have one output which is possibly being influenced by two inputs, like the total yield of a certain crop may be influenced both by the type of the crop as well as by the system of irrigation being used. The effect on the population mean that can be attributed to the levels of either factor alone is called a main effect. In our example, we can say that the type of the crop is a main effect and the type of the irrigation system is another main effect. We have two main effects. Apart from the main effects, we have a third type of effects which is called an interaction effect. An interaction effect between two factors is said to occur if the total effect at some pair of levels of the two factors or treatments differs significantly from the simple sum of the two main effects. Factors that do not interact are called additive, because for them the joint effect is simply obtained by adding the individual main effects. In our example, we shall have interaction effect if it so happens that some particular fertilizer is more suitable for some particular type of crop. If on the other hand, all the different types of irrigation have the same influence or at least similar influences on the different types of crops, then we would not have any interaction effect. Now, here are three questions that you can try to answer by using two-way analysis of variance. Are there any main effect factor because of factor A? Are there any main effect because of factor B? Are there any interaction effects between factors A and B? It might strike you as odd, but when we answer these questions, we must start by answering question 3 first, and if the answer of that is no, only then we can answer questions 1 and 2. If the answer to question 3 is yes, that is, we have interaction between A and B, then it is not possible to conclude anything about the main effects due to A and B separately. For example, we might investigate the effects on vacationers' ratings of resorts by looking at 5 different resorts. Thus, we have factor A, the different resorts, and 4 different resort attributes, factor B. In addition to the 5 main factor A treatment levels and the 4 main factor B treatment levels, there are 20 interaction levels. For example, in this case I have resort 1. For example, in this case I have resort 1, combined with attribute 1. Resort to combined with attribute 1. In this way, I have got 5 times 4 equal to 20 combinations. For each of those cells, we have one interaction effect. Of course, life is much simpler if we do not have interactions. So, let us first start by writing down the model for the case of two-way classification without interaction. Let us call the factors A and P and also assume that the number of levels of capital A is denoted by little a and the number of levels of factors capital B is denoted by small b. Then the model can be written as y I j equal to mu plus alpha I plus beta j plus epsilon I j. I going from 1 to little a, j going from 1 to little b. Let us understand the meanings of the different symbols used. Mu stands for the common mean or the overall mean effect. Alpha I is the effect of the ith level of capital A and beta j is the effect of the jth level of capital B. Epsilon ij's are of course assumed to be IID with normal 0 sigma square distribution and they are all identical and independent. Now, let us understand what is meant by mu. If we do not apply the effect of A at all and we do not apply the effect of B at all, and if we live in a world where there are no random errors, then the value that y I j would have taken, that would be just a constant, and it is this constant that we are taking as mu. We can write this system of equation in the form y equal to x beta plus epsilon, where beta transpose is the vector of all the parameters and the number of parameters is of course 1 plus a plus b, and you have to remember that because of unknown sigma square, the number of parameters is actually one more than what is written here. 1 plus a plus b is the number of coefficients. Sigma square is not a coefficient, but nevertheless it is a parameter. The vector y is the long vector consisting of all the observations or measurements. So, I write it as a long vector whose size is a times b. It starts with y 1 1 and goes on up to y a b. The b of course is wrongly typed here as s. Now, the normal equations, we all know about normal equations by now, are x transpose x beta equal to x transpose y. The capital X here is same as the little x that we saw earlier, but remember that capital A is not same as little a, capital B is not same as little b, but capital X is same as little x, and n is equal to a b, rank of x is a plus b minus 1. In case you are wondering how we got a plus b minus 1, I will just remind you that there are a plus b minus a, that is the rank of x. Now, normal equations can be written in a matrix notation which looks very neat, or if you want to make it look messier and more confusing, you can write them out using scalar notation, where you are not using any matrix, but explicitly writing the sums. So, a b mu plus summation x I plus summation beta j equal to y 0 0, and b mu plus alpha I plus summation beta j equal to y I 0, I from 1 to a. Remember, a here is little a and not capital A. Capital A is the name of the factor and little a is the number of levels of capital A. Similarly, you can get A mu plus summation alpha I plus summation beta j equal to y 0 j. Now, you may be wondering in the first equation from where did we get x i's. In the entire exposition there were no x i's. Yes, you will be right, it should not be x I, but you should be able to figure out what is the correct symbol that should be substituted for x I. Now, again if you look at the very last line and the first line, you will notice that they are essentially the same, which means that there is a mistake in either the first line or the third line, and it will be again an interesting exercise for you to figure out where the mistake is. Now, the estimable functions are obviously mu plus alpha I plus beta j for all I and j. Alpha I minus alpha I prime are also estimable if I is not equal to I prime, and if you think carefully you will understand that it is estimable even when I is equal to I prime, but that will be a trivial case. Similarly, about the betas, beta j minus beta j prime are estimable if j is not equal to j transpose, but actually it works even if j is equal to j prime. Now, suppose we pick a G inverse of x transpose x such that the solution vector becomes comma beta naught transpose equal to mu 0 alpha 1 0 etc. up to beta a 0. Do not be alarmed to see beta a 0, it should be actually beta b 0. We are sometimes writing little b for little a, with the understanding that we will know which subscript to use where. Now, again we have mu to the power 0 equal to a big thing, alpha I to the power 0 equal to a bigger thing. So, you should understand that mu to the power 0 is not undefined even if mu is equal to 0. Thus, we say in this case 0 is a superscript and not a power. So, beta j to the power 0 is also a similar expression. Now, this solution will satisfy the conditions summation alpha I to the power 0 equal to 0, summation beta j to the power 0 equal to 0. So, if summation alpha I to the power 0 is evaluated, in that case you will get alpha I to the power 0 is 1, because any non-zero number to the power 0 is defined to be 1. However, here the 0 is only a superscript. As a result, we can add all of them and still get 0. Now, we will need to compute the blue, and we already know what is meant by blue. Blue is the name of a color, but in this case blue does not stand for that color. Blue stands for best linear unbiased estimator. We shall find the blue of mu plus alpha I plus beta j, and that will be given by this expression. If I want to find out alpha I minus alpha I prime, then it will be the corresponding expression. If I want to find out the blue of beta j minus beta j prime, in that case again it will be a similar expression. So, you must be able to write down the blue of a given contrast very quickly just by recognizing the pattern. Now, SST, as we already know, is given by a big double summation of yij minus y00 bar whole square, and the DOF is equal to AB minus 1. What is meant by DOF? DOF actually is an abbreviation for do off, just as DON is an abbreviation for do on, but that DOF has a different spelling, which is spelled as DOFF. In this case, DOF stands for degrees of freedom. O stands for off, sometimes it is omitted. So, we say df equal to AB minus 1. SSE equal to summation alpha summation j of a very big expression, and as we have already mentioned in one of our earlier modules, we always continue to give a wrong expression in the hope that you will learn to write down the correct expression. So, figure out which of the negative signs should actually be a positive sign. Here the d of f is naturally a minus 1 into b minus 1. If you do not understand this, then try to read any standard book on linear models. Now, consider H naught alpha I equal to alpha for all I and beta j equal to beta for all j. Then use f equal to that complicated expression which has got q by a plus b minus 2 in the numerator and an even more hairy expression in the denominator, and this thing will follow f a plus b minus 2 comma a minus 1 times b minus 1 under H naught. This will allow you to do a testing, though you may not be clear about what alternative hypothesis you are testing against, but that is not very important as long as you can get a p-value from a software. However, if you really insist on knowing what you are testing, in that case consider testing H naught A, which is all the alpha i's are same, or alpha equal to alpha for all I, then QA is SSE of H naught A minus SSE. So, it is a big expression complete with our standard typo. Now, test H naught A using that big expression with degrees of freedom a minus 1 and a minus 1 times b minus 1. Similarly, consider testing the hypothesis for beta using QB, and you get degrees of freedom equal to b minus 1. Just as in the last case, we have degrees of freedom equal to a minus 1. Thus, you substitute b for a and you get the new expression. The two-way ANOVA model, I am writing it again, but using a different notation. Instead of gamma ij, I am writing alpha beta ij. Do not think that alpha beta is the product of alpha and beta, though even if you think like that, there will not be much difficulty, because anyway the remaining expressions will be equally confusing. So, let us consider alpha beta whole ij as the interaction effect of levels I and j, and alpha I and beta j are the effects of level I and level j respectively. Epsilon ijk are of course assumed IID with mean 0 and variance sigma square, and they are independent. So, all the other assumptions remain just as before. Now, we define a quantity called total deviation, which we shall write tot ij. Tot ij means difference between a data point and the grand mean yij minus y bar bar. You understand that if there are two subscripts, then we can write the overall mean as y bar bar. If there are three subscripts, we have to write y bar bar bar. If we have k subscripts, then we have to write k bars on top of y, which is somewhat difficult. So, it will be a good idea to keep k small, so that you can easily write things on a piece of paper. For any data point yij, tot is of course t plus e, that is total deviation is treatment deviation plus error deviation. Now, hypothesis tests are two-way ANOVA. Factor A main effects test are H naught alpha I equal to 0 for all I and H1 not all alpha I are 0. Factor B exactly similar but with betas in place of alphas, and B in place of A, and J in place of I. Just remember, you do not need to substitute J in place of I, because J is a dummy variable and so is I. So, you can even substitute A in place of I. For interactions, you can similarly test that all the alpha beta ij's are equal to 0, and the alternative is that they are not all 0. But as I have already mentioned, the last test must be done first. Only if it is accepted, you can proceed to test the earlier two sets of hypotheses. Now, we will find out the sums of squares. In a two-way ANOVA, yijk is a very complicated expression that we have seen already. The important thing here is that SST is SSTR plus SSE, and this can be seen very easily just by writing it out explicitly. Now, SST is equal to SSTR is split into three parts: SSA, SSB plus SSAB, and you can read the various hairy expressions with triple sums yourself. The case of one data point in every cell presents a problem in two-way ANOVA if we have interaction. There will be no degrees of freedom for the error term. What can be done? In that case, we can get rid of the error term. If we can assume that there are no interactions between the main effects, then we can use SSAB and its associated degrees of freedom in place of SSE. We can then conduct main effect test using MSAB. Two-way ANOVA with one observation gives rise to an ANOVA table which looks like this. I will not read out all the cells, you can read them for yourself. Just notice that there are 5 columns. The first is called SV. In most standard places, it is called source. Then SS, sum of squares, degrees of freedom, DF, mean squares, MS, and F ratio, which is obtained by dividing one MSA by another thing. So, this is the main idea of an ANOVA table. In most cases, you must have also another row for errors, which has been omitted here by mistake. We had already learned about one-way ANOVA, and in this lecture we learnt about two-way ANOVA. The theory of higher way ANOVAs are remarkably similar. So, once you have grasped the contents of this lecture, it will be quite easy for you to generalize the theory to three-way, four-way, or in general k-way ANOVA.